All right. Hi, everyone. Today it's a pleasure to have for the first talk of this year, Frans Pretorius from Princeton, who will tell us about open questions on the dynamics of black holes. So take it away, Frans. Thank you.
Okay, thank you very much. Thank you for the invitation, and also thank you very much for accommodating the time a little bit. That's it's been very helpful for me, so thank you. Okay, yes, I'm going to talk about some open questions on the dynamics of black holes. Um, let's see there, okay, yeah. Um, here's the outline of my talk. So I'll first, I guess to set the stage, I'll first describe a little bit of a background. So this is going to be about black hole dynamics. And sort of one of the main thrusts here is that the very different dynamics or kinematics that we get in general relativity in the so-called strong field versus weak field. So I'll start a little bit explaining, at least in my perspective, what strong field versus weak field are, and also say a little bit about everything we do know about black holes. And of course, that's a lot. So what we don't know in classical general relativity is perhaps a sliver of information. So there's a tremendous amount we do know. So to set the stage, I'll summarize a little bit of that before getting to some of the open questions. So with the open questions, I think, in my opinion, some of the most interesting open questions relate to nonlinear perturbations of near extremal black holes, ultrarelativistic limit of black hole collisions, and also black hole interiors. Um, Now, I know I've said sort of in the abstract that I was going to talk about both near extremal and ultrarelativistic, but I probably won't have time to get to the ultrarelativistic part. So this is sort of based on a talk that I've given sort of at the level of a physics department colloquium, but there was much more introductory material. So I thought I'd take out some of the introductory material and yes, spend a little bit more time at least looking at sort of concrete results in this toy problem. So unfortunately, there's not going to be anything in terms of answering the questions. But I added a little bit too much of that which I think might be more interesting for this audience. So depending on how I go, I might not actually get to the ultrarelativistic. Um, Nevertheless, most of the talk is sort of at the level of speculation. But hopefully I can convince you that there's some very interesting problems still in classical relativity. And then the one sort of some early steps, at least with a near extremal curve, to try to address some of these questions. Okay, so what's the motivation? Like, why spend so much time thinking about black holes? And it's theoretical curiosity, and really just the main motivation is to really understand in all of its rich and intricate details what is a black hole as described by Einstein's theory of relativity. So of course, like at one level, you can say, well, a black hole is sort of the generalization of a point particle in Newtonian gravity. And in Newtonian gravity, a point particle is, okay, it's an idealization and it's kind of a useful idealization in many respects. But if you say, well, in general relativity, if we have a point particle, you want to consider it as an idealization, that's inconsistent with the field equations. What you generically get is a black hole. And so you have to deal with black holes from the beginning. Now, certain aspects, in the far field regime, you can sort of ignore the black hole nature of the space-time. But if you really want to understand what the simplest kind of gravitational, strong field gravitational particle is in relativity, you have to understand what a black hole is. And of course, it's much more than just a point particle. It's got structure, and of course, it's a dynamical object as well. So a tremendously rich subject, and we want to understand as much about it as what we can in classical relativity. Okay, so again, this talk is restricted to pure classical gravity. So this is let's just take a step back and just get us all onto the same page. So, of course, this is about the Einstein field equations. The Einstein tensor, which is essentially geometry on the left-hand side, coupled to the stress energy tensor of any matter in the space-time. And so what I want to sort of get to is the strong field regime. So perhaps first let's describe, well, what is the weak field regime in general relativity? And very colloquially, of course, you can get much more technical about this. But I'll say the weak field regime of relativity is a solution to the Einstein field equation that starts from the completely flat asymptotically four-dimensional Minkowski solution. So plug in the Minkowski metric on the left-hand side without any stress tensor on the right-hand side. That is a solution to the Einstein equations. And now let's consider small perturbations of that. So now the perturbations can include matter. And all of that, in a very colloquial sense, I would call the weak field regime of the Einstein field equations. And of course, that is an incredibly rich part of general relativity, just by itself. Of course, in one limit, we recover special relativity, the Minkowski solution. We get Newtonian gravity with various interesting corrections. In that, in that limit, we also, recover that, or first learn that general relativity allows gravitational waves. We get the two polarizations. With the various approximations, you can also understand the energy content of the radiation, etc. The famous quadruple formula, etc. Okay, so is that consistent with nature and within the level of experiments and observations? And it seems that there's no experimental observational um, study. Okay, well, I'm ignoring dark energy and dark matter. If you want to think that they might be problems with GR, that's a viable idea. But barring that, there's really all observations and experiments seem to suggest that nature is well described in this weak field regime by general relativity. And perhaps, I'm giving you one example. I'd say perhaps in my opinion, the most spectacular is the binary pulsar. In particular, the Hulse-Taylor binary pulsar was the first one. And essentially, that's sort of you're measuring very accurately the orbital period of a binary pulsar system. So, except around the neutron star for the pulsar, most of this is weak field gravity. And so general relativity describes the corrections to the orbit. It describes the radiation that's being emitted by this orbital motion, and therefore by sort of conservation of energy, the decay of the orbit through the emission of gravitational radiation. Um, and all of this is consistent with the predictions. And I find, this particular example so spectacular in that the dots are the observations, and the line is not a fit to the data. It's actually the prediction of relativity, and to me, it's a very remarkable result. So, uh, so nature does seem to, or general relativity does seem to describe geometry or gravity in the weak field regime quite well. So what about the strong field regime? Okay, so the interesting thing about general relativity is that in the Einstein-Hilbert action, or just the field equations, there's no sort of quantity or parameter of scale length. So this is a theory about geometry, so that would be the relevant kind of characterization that you might look for. That would differentiate what you might consider strong field versus weak field. Well, there's no scale where we expect, at least based on that argument, for new dynamics, new qualitative dynamics to appear. So in sort of Newtonian gravity, you can say, what is strong gravity versus weak gravity? Well, there's nothing qualitatively different. It's just a stronger Newtonian field, a larger mass, for instance. And so you might say, well, the field equations don't have a length scale associated with them, so that must be the same. And of course, surprisingly and interestingly, that's not the case with general relativity. There definitely is a qualitatively different regime of solutions. And now, because it's not associated with any scale in the theory, it turns out that one way to think of where it's coming from is the nonlinear nature of the field equations. Essentially, that space-time perturbations can carry energy and that they will gravitate. And it's that nonlinearity that sort of imbues relativity with the strong field regime. And of course, that implies because there's no length scale associated with it, you can have strong field dynamics or kinematics at any particular scale. Then it becomes sort of more a question of initial conditions. And for example, with black holes, you can have them arbitrarily small, arbitrarily large in classical relativity. The curvature at the horizon can therefore be arbitrary, but horizon dynamics, if you want to consider that strong field, therefore can occur at any particular scale. Now, it's not easy, perhaps possible, to define this in a more precise way, except in certain limited situations. And one of them is in sort of spherical-like situations. And that's through Thorne's hoop conjecture. So there's no intrinsic scale in the field equations, but let's introduce a scale through initial conditions. So let's take some amount of energy or mass. So yeah, it can be matter or it can be pure space-time energy. But here in this diagram, I've just said, let's just take a bunch of matter and make it spherical-like. It doesn't have to be spherical. But then what the hoop conjecture will say is, well, let's characterize the strength of this matter by this parameter, the Schwarzschild radius. So the actual extent of this matter here is given by R. So that's the hoop of radius capital R that can in any direction encompass this matter. Then you compute this quantity, the Schwarzschild radius, And you say if the Schwarzschild radius is less than r, then you're in the weak field. If it's greater than r, you're in the strong field. Okay, so what happens to space-time? What qualitatively changes when you're in strong versus weak field? And in the strong field regime, what happens is space-time undergoes gravitational collapse. It's quite a catastrophic difference from just the weak field dynamics. So interior to the Schwarzschild radius, space-time becomes intrinsically dynamical. It flows towards some kind of a singularity. The interior becomes causally disconnected from the exterior. Um, and if you're just outside and you try to sort of send information back to the outside about what's going on, you get all these interesting phenomena like uh, large redshifts, time dilations that in the limit becomes infinite as you approach this boundary separating the dynamical interior from the exterior. And of course, everything that I've said here, what we mean is a black hole forms. Um,
Franz, can I ask?
yes.
So what is the conjecture?
So the Hoop conjecture. Okay, so let me just uh, so the original. So this is a slightly bastardized version of what Kip had actually intended. So when Kip first studied the Hoop conjecture, he was assuming that gravitational collapse was occurring. So this flow towards a singularity was happening. And his conjecture was, would a black hole form versus a naked singularity? And so he conjectured that if the matter is sort of spherical-like, such that you can have a spherical hoop that encloses in all directions, then an event horizon would form. If that wasn't the case, so it was very elongated, like a cylindrical-like collapse or a spindle, you'd still get a singularity, but there won't be a horizon, so it'd be a naked singularity. So the Hoop conjecture was essentially saying that, yes, you can form naked singularities in relativity if it's sufficiently far from spherical. And this, it's this little test would do that. So the way that I'm assuming cosmic censorship in some sense that let's say horizons form. I'm not yeah, but I'm not. I don't know. You might be able to form naked singularities, but the way that I'm using this more is, well, when is this gravitational collapse towards a singularity actually going to happen? And it's you have to get some concentration of energy that's sufficiently compact in all spherical-like directions that this criteria is satisfied. Yeah. Okay. Okay, so yeah, just one comment about sort of dynamical strong field. So, of course, once gravitational collapse happens, space-time is intrinsically dynamical. But when things settle down, the exterior can be static or stationary. But sort of in terms of dynamics, say perturbations of black holes, black hole mergers, what would be sort of the equivalent limit when the dynamical degrees of freedom become strong? And then, again, that's also very difficult to perhaps define, but one way you can say is perhaps, when the quadrupole formula breaks down, or if you have perturbative, the perturbative Einstein equations in a well-behaved gauge, if the perturbation becomes of order unity. And then interestingly, back of the envelope suggests, that when this happens, sort of the luminosity of some causal process, um, or just some process that you set up, approaches the Planck luminosity. And one of the interesting things, like I'm not talking about quantum effects here, but notice that the Planck luminosity doesn't contain any H. So this is just a purely, this is a thing that, or you perhaps say it's kind of surprising that somehow classical gravity perhaps knows about the Planck scale, but or it's just well, it's dimensional analysis. But then interestingly, if you say, well, if that happens, if you have some sort of region where the luminosity is this large, and you then say, well, how much energy would that contain? You apply the Hoop conjecture, roughly speaking, that would assume that you would get black hole formation. So in this dynamical regime, if you have, radiation that's being produced, in some sense, it will be censored if cosmic censorship is correct. Okay, so what do we know about the strong field regime? And of course we know a lot. So it's essentially everything that I've described about gravitational collapse, the way we think about black holes, that was actually discovered a long time ago. And perhaps sort of more the sort of the non-dynamical or perturbatively dynamical aspects of this was discovered mostly in the 60s and 70s, sort of what Kip called the golden age of general relativity. And that was where sort of this revolution of the understanding of black holes and strong field gravity occurred both sort of at the same time on the theoretical side, and observations were starting to suggest that this wasn't just a mathematical curiosity of the field equations, but there actually might be regions in the universe where this description of nature is important. So, you could spend whole semesters of study going over all the things that were discovered. So I've just cherry-picked a few highlights. So, of course, the singularity theorems of Penrose, that singularities are generic, some form of pathology is inevitable when gravitational collapse happens. The remarkable thing that, as complicated and messy as the interior is, the exterior asymptotes to an incredibly simple form, the uniqueness, no hair properties. And remarkably, we have the exact analytic solution for the vacuum case, the Kerr solution. And of course, then the black holes also seem to be thermodynamic. And of course, if you add quantum effects, it seems that it's not just a coincidence, with the Hawking radiation, etc. And again, back also in that time, from the observational side, that's where the first, stellar mass black hole candidates were discovered in our galaxy, and also sort of the realization that quasars were distant objects, and if they were therefore, the amount of energy that they emitted would be very difficult to describe them. Or using conventional physics, how could you power such incredibly luminous objects without supermassive black holes? Okay, so I think since the 60s and 70s, the circumstantial evidence that the universe does harbor black holes became, I would say, essentially incontrovertible. Of course, here, several years ago, the Nobel Prize was awarded for, the compact object in the center of our galaxy. And of course, they didn't quite say, this shows it's a black hole. They showed because these observations, this is the one on the right-hand side about the orbits around the center of our galaxy. It doesn't say that it's a black hole, but it's consistent with a black hole. So there's an object there that is so compact that we cannot explain it by any conventional physics if it was not a black hole. And of course, this Nobel Prize was also shared by Penrose with these singularity theorems on the nature of collapse. So I'd say, as of over the years, the evidence became very strong, but it's circumstantial because we're not really probing space-time itself. We can probe horizons, by any means, but this is more like evidence. Well, what else can it be? Of course, I think that changed 10 years ago now when LIGO started working and discovered the first gravitational wave emission from the merger of two black holes. And I think at this time now, the evidence is, of course, we can never prove anything like this in science, especially with these kinds of observations that happen at large distances. But now the gravitational waves that come from the collision of two black holes and the fact that the templates match relativity and there's yet been no detected residual. So I'm showing you on the top left, that's the first detection. And this one on the bottom is a signal to noise 80 event. The first one was about 25. And the signal to noise 80 event that they detected, I guess this year, which is very, very similar in terms of the black hole properties, but it's sort of a spectacularly loud event. I think everyone was very surprised that the first detection would be that loud. And this one, the SNR 100 era was sort of perhaps expected to be perhaps at the end of advanced LIGO. So the fact that we've got something like that close to it has been remarkably lucky. And what such a loud event allows you to do is say, well, how consistent is it with general relativity? And qualitatively, the fact that there's no detectable residual says that, yes, this is quite strong direct evidence that black holes do exist in nature as described by relativity. And it's about as direct as we can get because this is coming from the gravitational wave emission from space-time itself. So say the first, perhaps the first 50 years of relativity, there was a lot of confusion about the strong field. Then from the 60s onwards, the next, 30, 40 years, we really understood about, the strong field and how it might relate to the universe. And in the last, few decades, with LIGO building up to this, we've also got a very good handle on perhaps the most dynamical events that we can get in our universe, which is the collision of black holes. Okay, so with that, in classical GR, what don't we know about the dynamics of black holes? And here, of course, I'm going to say I'm restricting to asymptotically flat four-dimensional space-time. And when I say, like, what do we know? I'm using the very low bar of a sort of a physicist. So if you asked a mathematical relativist, they would say that there's actually, even, about the dynamics of a single Kerr black hole, there's still things that we don't know. So talking to my mathematical relativist colleagues, I think they are quite close to proving the nonlinear stability of the exterior of the Kerr space-time. And that's kind of the next holy grail at the level of mathematical rigor. So they're sort of still at the level of proving things for single black holes. So very far from binary dynamics or some of these nonlinear collapse problems. But I'm going to assume a lot of the things, from the level of a physicist, we can be a bit sloppier. So when I say things that assuming all of the things that we know, it's at that level of rigor. Okay, so at the level of that kind of sloppy rigor, what still don't we know? And here's sort of three things that I think that are quite interesting that we don't know, even qualitatively. One is the nonlinear perturbations of near extremal or extremal Kerr black holes, or generically, charged black holes as well. The generic outcome of ultrarelativistic collisions. So we know a lot, I would say, in the head-on collision limit, we kind of know what happens, but if you look at grazing collisions, we don't. And of course, the interior is a complete open question as well for the generic interior form from gravitational collapse. So as I said before, I've been hoping to say a little bit about the first two topics, but probably most of this talk is just going to be about nonlinear perturbations of near extremal. Okay, so what is interesting about near extremal black holes? Well, let me say, for the most part, all of these speculations are likely purely of theoretical interest. The one, with extremal, near extremal black holes, the one chance that some of these dynamics might be observable is if there are near extremal supermassive black holes out there, and there's an extreme mass ratio in spiral that occurs that we could observe with LISA in the future. And the reason is, if you think, well, why can't LIGO see any of these things? And the reason is that the kind of dynamics that I'll be talking about, we need to excite the dynamics of the near extremal black hole. And so even if somehow some astrophysical process can produce an extremal stellar mass black hole that's in the range where LIGO could see it, and you arrange a perfect situation where you have two extremal black holes, their spins are aligned with the orbital angular momentum. So that would be the configuration that will give you the maximum spin of the merger remnant. The issue is that these dynamics aren't excited by the orbital motion, so we have to wait for the merger. And the merger of two extremal black holes, at least extrapolating current numerical simulations, that merger remnant is sufficiently far from extremal that we won't see these interesting dynamics. So I think, if I recall, like the extrapolation is that, in this most perfectly aligned configuration, the remnant will have a spin of about 0.97. And some of these things that I'll talk about, the arguments suggest that you might need 4 nines or more to start seeing these things. Now, of course, if you say, well, how can a supermassive black hole be spun up to such a level? And then the reason why that might be interesting to observe this, if there's an emery, so a 10 to the 6, 10 to the 7 solar mass black hole with a 10 solar mass black hole spiraling in, that in spiral and merger could excite these dynamics and not push the supermassive black hole so far from extremal that we don't see these effects. But of course, then is nature going to give us such rapidly spinning supermassive black holes? And sort of accretion physics, I'm not an expert, but at least both from at least the current analytical and various simulations suggest that it might not be possible. But still, okay, so this might be a purely theoretical discussion, and there's perhaps a sliver of hope that if we don't understand accretion physics as we think we do, for instance, then perhaps nature can give us this in terms of an emery. Okay, but what do we understand about the dynamics of near extremal black holes? Well, we know a lot from linear theory, so that is well understood. And there are 3 aspects of the linear perturbations that suggest that something interesting might happen at the extremal limit. And that's these three things that I've written down here. One, so when you perturb a black hole, you get these sort of the resonant modes of the black hole, these sort of quasi-normal modes, and they damped oscillations. But an interesting thing is that for near extremal black, always as you approach extremality, the damping time of the dominant quasi-normal modes goes to zero. So it almost seems like they want to become normal modes. They don't in the limit, but the damping time becomes very, very, very small. Another interesting property is that for rotating black holes, and actually also for interactions with charged black holes, with charged fields, there's this phenomenon of superradiance. So for a Kerr black hole, for example, if it's spinning and you say implode a gravitational wave on it with some angular, YLM, LM structure, it's got a certain amount of angular velocity. You can think of it this gravitational wave. And if the black hole is spinning faster than that, as this wave interacts with the black hole, it can gain energy and angular momentum. So it can scatter off the black hole and extract energy from the black hole. That's a superradiance phenomenon. And that's you can just sort of think of it. It's not nothing surprising. Nothing is coming out of the black hole. It's just from the space-time energy around the black hole. Like you have a spinning wheel, you throw a little pebble on it, and it can fly off at a much larger speed than what you threw on it because it's gaining energy from the spin of the wheel, and this is kind of the same phenomenon. Okay, so that's a property of spinning black holes. The interesting thing is if you look at the sort of the frequency that marks the onset of superradiance, that actually becomes commensurate with this frequency of the so-called near zero damped quasi-normal modes as you approach extremality. So there's kind of a resonance that might appear based on this onset of superradiance and quasi-normal modes. And another thing, which I won't say much more about, well, I guess I will when we get to the results on the toy model of a Horizon Nordstrom black hole, is exactly extremal black holes are linearly unstable. This is this famous Aretakis instability discovered a decade or so ago by Aretakis. Okay, so exactly extremal black holes are linearly unstable. If cosmic censorship holds, then generically you'd push nonlinearities would push it away from extremality. But at least indication suggests that even if generically perturbations of extremal black holes become some subextremal, there could be a transient Aretakis-like instability. So you could see some effects of this instability before things are censored by a horizon. Okay, so that last point is, that's also a motivation for looking at nonlinear dynamics of near extremal. But let's just look at these first 2 points. So what do they sort of suggest about nonlinearity? And I'd say that they would suggest that conditions are perhaps favorable for some form of strong turbulence to develop on the horizon or around the horizon of a black hole when you perturb a near extremal black hole. So I put these things in quotes because I don't really know how to define turbulence, especially not for gravitational perturbations. But let's just say just use this kind of definition. That's if we have a non-linear system like we do with black holes. So they're non-linear. If you have a set of normal modes or quasi-normal modes, etc., if it's non-linear, you almost by definition have to have what I'm calling your weak turbulence. And that's just mode coupling, for instance. If you go to the next order in perturbation theory, there'll be some energy interaction between the modes, and a given mode can produce daughter modes, etc. So that does happen. But for strong turbulence and the kind of stuff that if you looked at it, like, clouds or smoke or things like that, and you see, well, that's turbulent dynamics. What has to happen is that this interaction between the various modes, there has to be a significant transfer of energy on some kind of a local dynamical timescale. So why do these two sort of these two aspects of the linear problem suggest that in the extremal limit, conditions might be more favorable for strong turbulence? And one is the fact that the damping rate of these quasi-normal modes becomes small. So if we're far from extremality, these quasi-normal modes, they damp very rapidly. And on a few light crossing times, they essentially are gone. So if you want sort of interesting nonlinear interactions, that disfavors that. The waves just don't sit around for long enough. So the longer that you can keep the dynamics of these perturbations going, the more chance there is that there's going to be some interesting interactions. Now, even in the case if you have a very slowly damped wave, black hole isn't a closed system. Black hole space-time isn't a closed system. Energy can escape to infinity. Energy can fall into the black hole. But the interesting thing about this onset of superradiance is from the linear level, the black hole looks like a mirror. So if at exactly the onset of superradiance at the linear level, no energy flux crosses the horizon. So it basically reflects everything. So there you shut down one channel of energy loss. So these things together might suggest that, okay, perhaps there could be some kind of strong turbulent dynamics on the ring down of a near extremal black hole. This is just speculation, but there's also some other evidence that suggests it might not be as crazy as it sounds. And one comes from the ADS CFT correspondence or black holes in Einstein gravity with the asymptotically ADS boundary conditions. Now, I mean, if you'd asked someone like a relativist like me, like 20 somewhat years ago, like can gravitational wave nonlinearities produce something that looks like fluid turbulence? I would have said no, because Einstein equations are nonlinear. Navier-Stokes is nonlinear, but they're very, very different kinds of nonlinearities. But then with the ADS CFT correspondence of string theory, there was at least certain classes of or like a certain limits. There was this conjecture that seems to be, holding up to scrutiny that classical Einstein gravity in a space-time that's asymptotically anti-de Sitter is due to a conformal field theory, a quantum conformal field theory living on the boundary. And that quantum field theory can have certain states that, in certain regimes are hydrodynamic-like. And in that hydrodynamic limit, there's a kind of thermal states as well. It's due to black hole states in pure classical Einstein gravity. And so if this duality does work, then there's something that is governed by hydrodynamics in some limit. And on the other side, it's due to something that's governed by black holes. And the hydrodynamic theory does have regimes where there's turbulence. And so people started to sort of suggest that, and Luis Lenner and people sort of argued for that. And then I'll show you this animation from Adams, Chesler, and Liu back in 2014. And again, this is the thing with the anti-de Sitter space boundary conditions is you can get different kinds of topologies for the horizon. So this thing is very different from a Kerr black hole in the sense that here you've got a black brane. But still, so this is showing a perturbation of this black brane horizon in pure classical Einstein gravity, but now an asymptotically anti-de Sitter boundary condition. And so what I'll show you, so okay, this is the perturbation. Now the quasi-normal modes, it's actually decaying, but they factored out the overall decay. But now you can start to see this nonlinear interaction happening. And like, what does it look like? It's the turbulent kind of a ring down that's happening on pure classical Einstein gravity for a black brane situation. Now, okay, so you might say, okay, that's very interesting. So Einstein gravity around horizons can have turbulent-like dynamics that develops, which is, you can map it also one-to-one to fluid dynamics on a corresponding boundary conformal fluid. And so so people have asked, well, is that possible for a Kerr black hole in asymptotically flat space-time? And of course, it's not clear.
But isn't as it decays, I know they factored out the decay, but as it decays, doesn't it become more and more linear?
Well, that's what you would think, but then all of the structure is developing, right? So, in a sense, this is a small perturbation, but it's saying that the nonlinearities relative to that decay are still sufficient to get all of the structure, right? And also like that's the thing that also like, okay, I don't, like fluid turbulence, etc. That also happens in situations when there's small perturbations, and that doesn't show up at the linear level, in hydrodynamics. So it's a fundamentally nonlinear problem that's not very easy to capture, especially not at sort of the perturbative level. So, but yes, I mean, this on the horizon, if you look at it in terms of various measures, these are very, very small perturbations, yet the structure is continuing to develop.
Okay.
Yeah.
So, but following up on this question, so do you have some other longer time scale for decay, or does it continue indefinitely?
Yes, yes. I'm not sure. So the overall decay will continue indefinitely. But I guess you're asking at some point, is there a transition to a thing where whatever turbulent structure has developed up to a point will then not continue. So there won't be a cascade to smaller scales or larger scales. Will that stop at some point? And I don't know. So yeah, so these, and because these are like the full Einstein equations, and it's a very complicated, expensive simulation. They couldn't resolve more than perhaps one order of magnitude of when they try to do Fourier analysis and try to see if they could get some kind of a scaling, Kolmogorov-like scaling, and it's very limited the range that you can do because these are very expensive simulations. So this hasn't been studied in much detail other than sort of this qualitative detail. Okay, then well, you say, well, okay, things are very different for Kerr black holes. First of all, ADS is confining. Energy can't escape with these kind of boundary conditions. So energy can only be lost through the horizon. And of course, a planar topology could be very different from the kind of Kerr two-sphere. But then, Yang, Zimmerman, and Lehner, they try to sort of use this gravity fluid correspondence to come up with some kind of an effective Reynolds number for a Kerr black hole. And again, they used the toy scalar field. They said, standard perturbation theory doesn't work. So it was a rather ad hoc way of trying to map what might be an effective Kerr-Reynolds number using a toy scalar field model. But nevertheless, so with all those caveats and grains of salt, they argued that you'd need perhaps 4 nines or higher to start to see this kind of effect on a Kerr black hole. Okay, so let me let me just also show this other thing about superradiance, another sort of interesting thing from a nonlinear study, and this is also quite a while ago. So a couple of students of mine back then, Will East and Fedi Ramazanoglu. And so we were actually trying to understand the nonlinear aspects of superradiance. So now doing the superradiance scattering problem, and we could only go up to A's of 0.99. So that seems like it's close, but I'll show you even some of the results that actually that's still very far from extremal in certain respects. We were actually just wanting to see like what happens if we now sort of look at the superradiant problem, but with a very large amplitude gravitational wave. So the wave contains perhaps 10% of the mass of the space-time. This is just an animation just to show what's happening. So here, that little Mentos-like peppermint in the center, that's the horizon, the apparent horizon. The blue is the coloring is, so we're looking at psi4 and psi0, the ingoing and outgoing radiation as measured by Newman-Penrose scalars. Blue is sort of ingoing radiation, red is outgoing radiation. This is the dominant quadrupole L equals M equals 2 wave that we're imploding on the black hole. And so as I play the animation, you'll see that the white horizon start to rotate. But of course, it's always rotating, but you don't see the rotation because it's axisymmetric until the wave implodes. Then it starts distorting the horizon. And so you can see the rotation just because it's being distorted, but it's always rotating. Okay, so this is our initial conditions. The wave comes in. You can see there it starts to, well, then you can see the rotation. So it's perturbing the horizon. And this is now a superradiant case. Of course, you can't see it from the colors, but here it's extracted some fraction of the energy of the horizon and scattered outwards. So let me just show you sort of the main takeaways in terms of this problem. So what I'm showing you here is measurements of the apparent horizon, so the dynamical horizon, for three frequencies of the wave. One, so the maximum superradiant frequency for this particular black hole, one that's much greater than the superradiant. So this is more like an accretion problem. And then one that's at the onset of superradiance. So these 3 panels are this top one is the gravitational mass of the black hole. This MIR is the irreducible mass. So this is the area. So this is the thing that has to increase. This is the area theorem. Any interaction, it has to increase. And J is the angular momentum. So first of all, just with this area increase thing, so this kind of jaggediness sort of at around 50 in this time units, that's just our numerical problems with trying to find the apparent horizon. So that the reason why we couldn't go to higher spin or higher energies here is that when we try to do that, at around the time when there's the strongest interaction with a black hole, our apparent horizon finder starts to struggle. So the area isn't decreasing. This is just numerical error. But then once the wave passes, things settle down. And so we do get consistency with the area theorem. But if we try to push it to larger amplitudes or longer interactions, our parent horizon find or higher spins, it would fail, and then soon afterwards the code would crash. If we can't keep track of the horizon, our excision doesn't work. Okay, but let's look at the super radiant case, so this black curve. So you can see that in terms of the gravitational mass, after the interaction, it's decreased, and the spin is decreased. So of course, total energy is conserved. So this is the case here. The wave has carried away more energy. In the subradiant case, the black hole gains spin and energy because it's sort of more accreting. And of course, at the onset of superradiance, this is kind of the mildest situation in terms of the change of the properties of the black hole. So there's some increase in mass, some increase in spin and area, but it's kind of the mildest. But now with getting back to sort of the interesting, perhaps nonlinear dynamics that might occur as we approach extremality, if we actually look at what's happening on the horizon, this red curve, this onset of superradiance, that's the largest dynamics that we see. So for example, here we measure two properties of sort of the geometry of the horizon. The top one is the ratio of the proper polar circumference to equatorial circumference, and the bottom is the induced uh, two-dimensional curvature, the two-dimensional curvature on the horizon. And you can see this red curve, which here again, this was, if you just looked at these plots of the asymptotic properties, if you will, you'd say that's the most mild case. But if you actually look at what's happening with the horizon, that's where this largest dynamics are happening. And so also just interesting to say, well, how far are we from extremal? If we had an extremal black hole, this dashed, I guess, sort of pinkish line, that would be the ratios for an extremal black hole and also the induced curvature. So you can kind of see that you might think 0.99 is close to 1, and in some respects it is, but in this measure, we're actually still far from extremal. So it's kind of interesting in the sense that at this onset of superradiance, there's the least transfer of energy and angular momentum between this interacting scalar field and the black hole, but there's the largest dynamics on the horizon. So it's almost like, if we could approach extremality and drive a black hole with a wave that's sort of tuned to the onset, we can perhaps excite a zero mode in some sense. If my guess would be if there's some way to violate cosmic censorship with Kerr black holes, it would be in this limit by driving it at the resonant frequency. It's not like you'll destroy the horizon, but you might be able to create very large curvatures near the horizon that you could perhaps drive to infinity in some fine-tuned sense. Okay, so I think hopefully I've convinced you that, so I guess, so again, this most of the talk, so yeah, I've got a little bit of time so I can explain some of the results of this toy problem, but hopefully I've convinced you that, near extremal perturbations seem very, very interesting, and it'd be worthwhile to try to push to get towards this limit. Like can we actually, what does the Einstein equations actually tell us? Can we get to large nines with nonlinear perturbations? And it's a very difficult problem, both analytically and numerically for various reasons. So unfortunately, I can't give you any results that might help clarify some of these things. But what we've decided to do is sort of take a set of smaller steps to get to that problem. So the first thing I'd say is, you might ask, well, why don't all these methods that have worked so well for binary black hole mergers, essentially, why can't we just try it and apply it? And that's what we did. So the study with Will East and Fethy, that's exactly what we tried to do. But for various reasons, like I said, one was just the nature of the apparent horizon, but these codes aren't well adapted to studying near horizon dynamics. They're Cartesian based essentially. They're Cauchy problems, and of course that's kind of what you want to do if you want to look at binary mergers. But if you actually think about it, if this is such a delicate regime to get to, you kind of want to make the numerics as well adapted to that problem as you can. And if you think about it a little bit, and this is what this sort of slide sort of suggests, is that if we are interested in sort of a single black hole near extreme, we'll understand what happens sort of in this case, perhaps the simplest way to look at this dynamics will be with a scattering driven wave problem. We really want a characteristic code. So we want to use coordinates that are adapted to the characteristic structure. So I've shown here on the right side, and essentially because, of course, the boundaries of the space-time that are of most interest are null boundaries, they're characteristic. So the horizon itself, Of course, we want to look at things at future null infinity. Eventually, if you want to look at interiors, for rotating black holes, we want to go to the Cauchy horizon, this R equals R minus, so all null boundaries. And from the initial data perspective, it's much easier to impose boundaries on scry minus, sorry, initial conditions on scry minus. So actually, for example, one of the problems with the Cauchy code, another reason why we couldn't go much beyond 0.99 is the current ways in which we solve the constraints for Cauchy codes is with this conformal approach, the Euclid-Nurowitz type conformal approach. So we specify some ingoing train of data on some t equals constant surface. And then to get a consistent solution, we solve the Hamiltonian momentum constraints. But those are elliptic equations. And so if we start with a black hole that's, say, 0.999, and then we have a wave train, we solve the constraints, that the actual black hole that we get is usually pushed away from extremality. So the current way of imposing initial data on Cauchy codes, that also limits how close to extremality you can get. With characteristic codes, if you put data on scry minus, that the structure of the Einstein equations are completely different. This problem doesn't arise at all. So lots of reasons why we'd want to use a characteristic code. And right now there are no generic three-dimensional characteristic codes adapted to this. So a lot of work was done back in the Grand Challenge days, the 90s, by Jeff Winnicker's group, Luis Lehner. So they did do a little bit of that. But then once we could get Cauchy codes, that kind of was put on the back burner. So we kind of have to start from scratch with these Cauchy codes. So that's a daunting problem. So let's say, well, let's try to get there in a few steps. And so this is this one toy problem that I'll mention a little bit about. So this is work with grad student Zach Gals. And so we said, well, let's start with the simplest system as possible that's got some of these properties of near extremal black holes that might be interesting. And of course, luckily, there is an example which we can use in spherical symmetry, and that's with the charged black hole. So now, of course, if we wanted to do this with Kerr, we'd have to immediately start at least in axisymmetry because a Kerr space-time is axisymmetric, and that's difficult. So with Rice and Nordstrom, the spherically symmetric, black holes, there is an extremal limit that's spherically symmetric. The spherically symmetric, extremely charged Rice and Nordstrom problem. And with a charged scalar field, it does have superradiance and we have extremality. So at least if qualitatively, that's the important thing. If the kind of nonlinearities that we see in the limit of extremality really just depends on the surface gravity of the horizon and the fact that there is superradiance, we hopefully can start understanding this with this toy model without going to the more complicated Kerr vacuum case. So that's what we wanted to do. But even so, it's a non-trivial process. So we decided to actually break it down into a couple of steps. So first, looking at charged massless scalar field dynamics on a fixed Reisner-Nordstrom background. And that's what I'll give you some results on. And that's actually been a problem that's been studied quite a lot before. And then currently we're including back reaction, and Zach is pretty close to getting some results, but unfortunately not close enough for this talk, but he should have some results soon with back reaction. And essentially, this is also very close to what these authors below did. So they did look at the full back reacting problem, but with an uncharged scalar field. This is what I'm going to be describing. Most of what I'll show has been known before. So we're just adding a few little points to this thing. But again, we're taking through little steps to hopefully make the eventual problem more manageable. Okay, so what are some of the key properties of this Einstein-Maxwell-Klein-Gordon system? Well, one is just sort of this big caveat. So again, we're interested in eventually generic perturbations. And the one thing that we have to be worried about with what is a spherically symmetric model going to be telling us, or what might it not be telling us? And of course, the one problem is in spherical symmetry, there's no gravitational dynamics. All of the dynamics of the problem is driven by the matter, and in this case, by the scalar field. So, whether a scalar field propagating on an extremal black hole with back reaction or not tells us something about the full problem, that's an open question. At least with respect to the Aretakis instability, it does seem to be a good model. So it captures that, the qualitative behavior, at that level. So it might be good enough, but that's a caveat to keep in mind. Another interesting thing now, just with this particular complex scalar field that we are using is that there are three distinct regimes. So the one, and I'll show you it'll be easier to just show you with the actual results, but one essentially eases the coupling constant in the Lagrangian. Q naught is the charge of the background black hole. So we're using units where m, the mass is 1. So Q equals m equals 1 is the extremal case. So if this ratio is greater than half, we have so-called strongly coupled, weakly coupled, and of course, if it's 0, it's chargeless. But the interesting thing is that the limit to the charged case is not a uniform limit. So taking small e cases and extrapolating to e equals 0 does not give chargeless solutions. Another complication is that even if now we're restricting to a fixed background, the Maxwell charge scalar field equations are nonlinear. And so even though, that might be an interesting problem in its own right to look at those nonlinearities, but we want to avoid, eventually we want the full Einstein dynamics. And so we didn't want to deal with a situation of like, if the charge, say, from the perspective of the Maxwell field becomes very different from the charge of the Rice-Nordstrom solution, what does that mean? Of course, if you do the full self-consistent solutions, they will be consistent. So for this study, we just restricted to small perturbations. So even though it's a nonlinear problem, we kind of chose initial conditions such that we were in the linear regime. Okay, so the setup is, so we're going to look at the scattering problem. So we're going to start with the black hole. And here we're essentially going to put initial data, not quite at scry minus, but on the surface NB. And so I'm going to show you results from two classes of initial data. One, which is a sort of a small amplitude perturbation. So like a pulse of radiation is going to come in, going to perturb the black hole. And then we're going to look at the quasi-normal modes, the power law decays, etc., and what happens. And then the cases of weak coupling versus strong coupling, near extremal versus extremal. And essentially what this thing on the right says is that, sort of the frequency of this complex field we can relate, in this case, for a monochromatic wave relates to this charge coupling. And at least later for the scattering problem, this omega tilde equals E will be the onset of superradiance as well. And here the superradiance it's not angular momentum, it's the charge. And so, below and above this threshold, you can get the same things where you extract charge and energy from the black hole. Okay, so again, as I said, this is not a new problem at all. It's been studied for decades. And so this very, very busy table, kind of just to show like everything that has been known before. And those results in blue are kind of the things that are new to this study. And even so, like, especially in hindsight, a lot of the work that had been done before, would have been pretty straightforward to come up with these sort of decay things just without doing much work. But in any case, the things that are, at least as far as we could find in terms of published material, the novel things are those blue highlights. So what this table is showing you is essentially the late time decay of the scalar field at both the horizon and at null infinity with various values of these particular parameters. So this is sort of, if you will, the power law tails either on the horizon or at infinity. And of course, with the charged field, then we can also look not just at the scalar field itself in these first two rows, but the energy density, so the first three rows, the energy density, and then also the charge density. So the columns are, so the Q is the sub-extremal chargeless case, sub-extremal charged field, extremal chargeless, sort of extremal uncharged. And here this H naught is something to do with the Aristarchus instability, which I won't mention. And then, of course, the extremal and charged field case. So these V and U are the Eddington-Finkelstein-like coordinates, and these sort of show the rates of decay. And rather than sort of try to sort of mentally parse what these various decays are, I think it'll just be easier just to show the results. Oh, and incidentally, this difference between strong and weak coupling is sort of conveniently characterized by this S parameter. That essentially the weak coupled case is 1. As you increase the coupling, it goes down to half and then it saturates. So if you increase it beyond that point, this parameter S stays at exactly a half, and that's a strongly coupled case. Okay, so let's look at the results. So let's first start with this scalar field perturbation on a near extremal horizon. So this Q naught is 3 nines, and with chargeless below, weakly coupled and strongly coupled. So here, what you can see, what happens is as you increase the first, if going from chargeless to the charged case, the decay slows down. So you can see we get for initially, these oscillations are quasi-normal mode type oscillations. And then you transition to this power law decay. And essentially these exponents, this is the Eddington-Finkelstein time on the horizon. This exactly corresponds to the parameters on the previous table. If you plugged in the various S's, you find it's consistent with that. So the difference, you can see the rate of decay significantly slows down when you go to the charged case, and it slows down further when you go to strongly coupled versus weakly coupled. Okay, now if we go to the extremal case, so extremal background, now Q equals 1, we see the same trends. But interestingly, also, if you flip back and forth, or perhaps just look at this is the slowest case that you get with sub-extremal, it's v to the -1. The extremal case, it's now even slower at v to the -half. So, adding charge, going to strongly coupled, and going to extremal, all of that slows down the decay on the horizon. And of course, that's essentially, the thing, the problem with the Aristarchus instability. If there's slow decay, there's possibility of instability, and there's also then a possibility for interesting nonlinear effects. Now, one interesting thing that happens, so I mentioned, so these, if you say, like, we've got this in the limit of extremality, the quasi-normal decay rate goes to 0. And so one thing, at least when I first started looking at this in more detail, I was sort of naive and sort of assumed, well, that meant that in the extremal limit, they become normal modes. If the decay rate goes to 0, you've got normal oscillations of an extremal black hole, but that's wrong. And I think that's also part of the terminology, calling them zero damp modes. The thing is, in the extremal limit, or perhaps one way of understanding this is if you look at the Green's function of the linear theory. So the quasi-normal modes you can sort of understand as coming from these poles in the complex plane. Now, for any black hole, there's a branch cut at omega equals 0 on the real axis. So the imaginary axis, omega real equals 0. And one way of thinking is that the branch cut gives you the usual power law decay. But at these so-called zero damp modes, what happens is that the poles in the complex plane become closer and closer spaced together. And so in the extremal limit, they merge into a new branch cut. And so that's why at exact extremality, you don't have normal modes, but now you've got a new branch cut. So you've got a new set of sort of a new possibility for power law decay. And that sort of dominates at late times. But then interestingly, if we sort of looked in sort of fine detail of this sort of decay, we could see this kind of oscillation occurring on the decay. And what it appears to be is sort of an interference effect between these two branch cuts. Just sort of like in this case, what you see here with a quasi-normal mode decay, that's actually interference between the leading and the subdominant quasi-normal mode that we see. And here we sort of see an interference effect between the two branch cuts that are sort of governing this quasi-normal behavior. So kind of, it's a very subdominant effect, but it's kind of interesting that that's kind of the analog of interference between two quasi-normal modes. These branch cuts are producing sort of some interference effect. Okay, so now let's go to the horizon. So these two plots were, okay, that was also at the horizon, but now let's look at the energy density. So the interesting thing is with sub-extremal, these all the energy density decays. If you now look at the extremal case, if it's uncharged, the energy density also decays, but the energy density actually grows for the charged field, and it grows most rapidly for the strongly coupled case. And then if we look at the charge density on the horizon, interestingly, okay, it also decays for sub-extremal. It actually also decays for weakly coupled, but for the strongly coupled case, it actually asymptotes to a constant. So this is kind of interesting. And again, I don't think this was noted before in the literature, but from the results before, if you did some back of the envelope calculations, you could have sort of inferred that. But it's kind of interesting seeing this sort of explicitly that in the strongly coupled case, in some sense, the black hole develops a new kind of a charged hair in the extremal case, that there's a sort of a charged shell that forms on the horizon in the extremal case. Okay, yeah, sorry, that has been an hour. So let me just very quickly go past the driven problem. So now in some sense, we want to look at a monochromatic wave. And again, let me just cut to the chase and say that, like what is something interestingly happening at the onset of superradiance, and this blue curve. So now we have a very low amplitude monochromatic wave that we're just spreading for a long time. And again, we don't want to go for long enough that the maximal nonlinearity has become important. But yeah, you can see at the onset of superradiance on the horizon, we get the essentially growth of energy density and charge, whereas the other ones are much more regulated and mild. So the scattering problem, can we break a black hole by exciting it at its resonant frequency, at least, without back reaction? This is a very interesting frequency in the charged case. Okay, and then, I won't say anything about the scattering problems. Let me just go to the conclusion. So at least hopefully, okay, so, this is mostly a sort of a speculative type talk. Hopefully I think we're living in a very interesting time. We know so much about black holes, and we're kind of in a new golden age where we're learning about the universe through the dynamical strong field. And that's gonna continue. I think we're just in early days of learning about it. If you think about what don't we know for the next generation or LISA, etc., it's most likely just in terms of waveform accuracy. So if we anticipate signal to noises in the hundreds or thousands, at the moment we just don't have the waveforms that are accurate enough. So we'll lose science if we don't get very high accuracy results for merger waveforms. But in some sense, that's sort of question about fundamental physics. That's sort of an engineering problem in some sense. But hopefully I've been in this talk been able to sort of show that just from a fundamental physics classical perspective, there are actually still some very interesting open questions in classical Einstein gravity as it relates to black holes. Sorry that I didn't have time to talk about the black hole collision problem, and of course not interiors, but I think the time is right. We kind of have the tools, and perhaps the time as well. Now that sort of a lot of the necessary development for the gravitational wave detection problem is sort of out of the way, that some of us can sort of go back to some of these fundamental questions, and there might be some very rich answers and surprising answers that we get, or at least I hope so. Thank you for your time.
Thank you, Frans. A great talk. Any questions?
Yes, I have a question. Can you hear me?
Yes.
Thank you, Frans, thanks much for the talk and for the ambitious perspective. And I would like to make two comments. First, you mentioned the golden age, and you mentioned it again in the conclusions. I think we should realize that we are now in a second golden age, at least as far as observations are concerned. One looks at the observational achievements. A while ago, the appreciation of the content of cosmology of the energy density, and more in the recent decade, the gravitational wave discovery and the black hole images. So I think we have a golden age, which is driven in gravitational physics, which is driven by observations. That's my first comment. The second one concerns the open questions that you mentioned also in your conclusions and challenges. And I would completely agree that these are fascinating questions. But if you intended to claim that these are the only fascinating questions or the most interesting ones, then that's open for debate, I would say, because first, it's very hard to predict, and especially the future. And secondly, I can come up with several very interesting problems, even in black hole part of GR. The first would be, for example, finding the point particle effective action of a black hole. That is, what are all the effective interactions of a black hole with its environment? So that would include tidal coefficients, namely love numbers, and many other coefficients that we're not aware of so far. So they would be in a sequence of hierarchies. They could become more and more relevant. So this is one example of a problem that I'm not working on at present, but I think it's an important open problem in black hole physics. So these are my two comments about the golden age and about open challenges.
Oh, thank you. I agree completely. Yes. And yeah, I guess I should have said more strongly that this is definitely my bias towards the open questions. And I agree very much about the question that we're in a new golden age. And so, I mean, the way that I sort of think about this is kind of analogy with the cosmic microwave background. If you think like from the first discovery of, Penzias and Wilson and perhaps Kobe to everything that's happened until now in cosmology, it's been a tremendous set of advances to where cosmology is now a precision science. And I think that, in a sense with gravitational waves, and then also you say like imaging of supermassive black holes, etc. We're kind of in the early days still. I would perhaps not Penzias and Wilson early, but perhaps Kobe early. And if just that sort of track proceeds, I think the next 20, 30 years are going to be fascinating. And to young people should be very encouraged about this. Yeah, they don't want to get the impression that there's nothing left to learn. It's kind of the opposite, but it's the observationally driven side that's so very exciting.
All right. Any more questions? Well, so I have one actually. So you were talking about exciting rotating extremal black holes at the super radiant bound, and kind of that this could be the avenue to creating large curvatures near the horizon, using such like driving such black holes from the outside. So first of all, the question is this kind of the analog of what you did with the charged black holes? Is this kind of the analog of the accumulation of charge on the horizon? And the second, okay, so and the second question is whether there's any kind of astrophysical or scenario in which you can imagine such a thing, such an excitation for a rapidly rotating black hole, even semi-realistic.
Yeah. Yeah, so it is the analog, and perhaps let's say, okay, so a couple of comments. So one is to mention like with this Aretakis instability. So originally it's more like with gradients of fields as you cross the horizon. So with the Aretakis instability of exact extremal black holes, in some sense you don't see it from the outside, but it's sort of something that happens as you cross the horizon. But more recently, mathematicians Dejan Stojkovic, if I remember the name, and collaborators showed that. So the regional analysis of Aretakis was like axisymmetry, no azimuthal modes. But when they included azimuthal modes, they found stronger instabilities. And then if you sort of see that, like the results that I showed with Will East and Fedi Ramazanoglu, so that was with an L equals M equals 2 mode. So there is azimuthal, we're not in symmetry situations. And we saw those very large oscillations develop on the horizon. So I think, yeah, in that sense, that is sort of where I expect there might be some, in this kind of a driven problem, if you can sort of excite one of these high LM modes, perhaps it's in the very high LM limit, you can perhaps get very, very large curvatures to form probably on the equator just outside the horizon. And that might not be infinite. Of course, if you have back reaction, there's always going to be an interplay between probably the back reaction will only push you away from extremality to regulate this. But there might be some very fine-tuned kind of initial data where you could actually get those perturbations to become very, very large, perhaps even a singularity forming outside in some limit. But like what the Aretakis type results have shown is that even if you expect that it's going to be regulated, there could be a transient period where there's a significant growth of these quantities. And so that might be the thing that's perhaps more practically observable. And so then the question is there a situation where one, there's a near extremal black hole, and can something in some resonant sense excite this? And I think that the hope is, the one sliver of hope is that extreme mass ratio in spiral. Because as if you have, let's say, an equatorial orbit, that would be the best case, but probably generically any orbit might work. But as you have this little body spiraling in, the orbital motion actually, as it approaches the ISCO, which sort of in the extremal limit shrinks to the horizon, that frequency also becomes commensurate with these others. So you can sort of imagine that that could be something to excite the resonance. But even if that's not efficient, eventually when it does plunge, that will excite the quasi-normal modes at those frequencies. And so, the very sliver of hope is that if there is a 0.49 or higher supermassive extremal black hole, and LISA can see an Emery in spiral, the ring down, I mean, it's not going to be a naked singularity. It's not going to be anything too spectacular, but it might be that we'll start to see some very interesting ring down dynamics that is sort of a sign of what of some of these nonlinear effects that happen. And again, that's more of a hope. It might actually be that perhaps this limit is not as interesting as I think it might be, and it's the linear theories kind of giving us everything. And the nonlinear stuff might just be at the level of mode coupling and things like that. But that might be a case where we could perhaps observe these kinds of effects.
Thank you. All right, any further questions? Okay, if not, let's thank Frans again.
Thank you.
Close the recording.
Thank you. Thank you.